Welcome, deep divers. Ever just, stop to think about the invisible stuff holding our world together?
It's fascinating when you do.
Like, what makes a diamond so incredibly hard, but the graphite in your pencil, same element, carbon, is soft and slippery?
hmm
Or why is beach sand solid, but carbon dioxide, which you breathe out, is a gas? Even though, their elements are practically neighbors on the periodic table.
Yeah, those aren't just quirks. Those big differences in how things feel or behave, chips a bunch, it all comes down to one thing: how atoms connect.
The bonds between them.
Exactly. It's like the hidden blueprint for, well, everything.
So today we're diving deep into chemical bonding. We're using Chapter 8 of Zumdahl, and DeCoste's chemistry as our guide.
Yep. And our mission really is to pull back the curtain on how these connections work, how they shape rocks, us, our bodies, even how animals talk to each other chemically.
We want to make sense of these connections, give you those aha moments about the world, but without just drowning you in details.
Right, because this isn't just abstract theory. Understanding bonds helps make sense of, well, how medicines work, why metals conduct electricity, how life itself functions at a molecular level.
It really is a shortcut to understanding that hidden architecture. Okay, let's start at the beginning then. What is a chemical bond, fundamentally?
At its simplest, it's the force holding atoms together, making them act like a unit.
Okay.
But the why is maybe more interesting. It's all about energy. Nature prefers things to be in the lowest possible energy state, more stable.
Like water flowing downhill.
Pretty much. Atoms stick together if being together puts them in a lower energy, more stable state than being apart.
So it's a natural tendency towards stability.
Yeah.
Makes sense. And you mentioned there's a range of these connections,
Yeah.
a spectrum.
Absolutely. Let's look at the extremes first. On one end, you've got ionic bonding.
Okay.
It's like a dramatic electron heist. One atom, usually a metal, basically gives away an electron or two. Another atom, typically a nonmetal, really wants to grab them.
So you end up with charged particles, ions.
Precisely. A positive one, the cation, and a negative one, the anion. Opposites attract, right?
Like table salt, sodium chloride.
Perfect example.
Yeah.
Sodium Na happily gives up an electron. Chlorine, Cl, eagerly takes it. Now you have Na plus and Cl, and that attraction isn't just one-on-one.
Right, they form crystals.
They pack together in a highly ordered structure, a crystal lattice. And the forces holding them there, these electrostatic attractions, are strong. That's why salt is solid, hard, melts at a high temperature.
And the strength depends on the charges.
Yep, and the distance. Bigger charges, closer ions, stronger attraction. That's Coulomb's law in action, essentially.
Okay, so that's one extreme of the transfer. What's the other end of the spectrum?
That would be covalent bonding. Here, it's all about sharing electrons. Think about two identical atoms, maybe two hydrogens.
H2 gas.
Exactly. As they get closer, their electrons start being attracted to both nuclei. There's this sweet spot, a specific distance.
The bond length.
That's it. Where the attractions between electrons and nuclei are perfectly balanced against the repulsions, nuclei repelling nuclei, electrons repelling electrons. At that distance, the energy is at its minimum. The H2 molecule is stable.
So the shared electrons act like a glue holding the nuclei together.
Pretty good way to think about it, yeah.
But what if the atoms aren't identical? They don't want to share equally, maybe, but they don't fully transfer either.
Now you're hitting the middle ground.
Yeah.
And frankly, most bonds live here. This is polar covalent bonding.
Polar, meaning like poles on a magnet.
Sort of. Think about hydrogen fluoride. Here, fluorine is much more electron hungry than hydrogen.
It cools harder on the shared electrons.
It really does. So the electrons spend more time closer to the fluorine. This gives the fluorine a slight negative charge, we call it delta minus, and leaves the hydrogen slightly positive, delta plus.
Partial charges.
Exactly. And because of this charge separation, the whole HF molecule acts like a tiny magnet. If you put it in an electric field, it'll actually line up as a positive end and a negative end.
So this unequal sharing has real consequences for how the molecule behaves.
Huge consequences.
Okay, this electron hunger you mentioned. There's a way to measure that, right?
There is. It's called electronegativity. It's basically a measure of how strongly an atom in a molecule pulls shared electrons towards itself.
Like it's tugging power in that electron tug of war.
That's a great analogy. And yeah, there are trends on the periodic table.
Right. As you go across a row, it generally increases. And down a group, it decreases.
You got it. Fluorine, top right, is the champ. Highest electronegativity. Cesium, bottom left, barely pulls at all.
And the difference in this pulling power between two bonded atoms tells us about the bond type.
Absolutely key.
Hmm.
If the difference is zero,
Yeah.
like an HH, they pull equally. That's a pure covalent bond. If the difference is really big, one atom basically wins the tug of war completely that's ionic.
And everything in between.
Is polar covalent. The bigger the difference, the more polar the bond, the more ionic character it has. It's a sliding scale.
So for everyone listening, quick mental check. Think about these bonds, HSH, CLH, OHFH. Can you rank them by how polar they are, just based on where those atoms are on the table, least polar to most polar?
Take a second. HH is zero difference, right? Nonpolar. Then sulfur is pretty close to hydrogen, so SH is only slightly polar. Chlorine's further right.
So CLH is more polar.
Yep. Then oxygen is even more electronegative than chlorine.
OH, more polar still.
And finally, fluorine, the most electronegative element.
FH must be the most polar of that set.
Exactly. The electronegativity differences increase, 0, then about 0.4, 0.9, 1.4, and finally 1.9 for FH. That difference directly tracks the polarity.
That's cool how a simple number helps predict so much. Okay, so that's individual bonds, but molecules are collections of bonds. How does this polarity play out for the whole molecule?
That's where dipole moments come in. If a molecule overall has a separation of charge, a distinct positive end and a negative end, it has a dipole moment.
Like the HF molecule you mentioned.
Yes. We often draw it as an arrow pointing towards the negative end. But here's the crucial part.
The shape.
The three-dimensional shape of the molecule is critical. You can have very polar bonds, but if they're arranged symmetrically, their effects can cancel each other out.
Like in carbon dioxide, CO2.
Perfect example. CO2 is linear, OCO. You have two strong polar bonds, carbon-oxygen, but they point in exactly opposite directions.
180 degrees apart.
Right. So the poles cancel. Imagine two equally strong people pulling a rope opposite ways, nothing moves. CO2, despite its polar bonds, is a nonpolar molecule. No overall dipole moment.
But water, H2O, is different. It's bent.
Yes. That V-shape is key. The two polar OH bonds don't point directly opposite each other. They point sort of upwards towards the oxygen, if you imagine it that way.
The poles don't cancel.
They don't. They add up, creating a net pull towards the oxygen. Water has a significant dipole moment. That's why it's such a good solvent, why ice floats. All sorts of unique properties stem from that polarity and shape.
And methane, CH4, carbon with 4 hydrogens around it.
Methane's interesting. The CH bonds are slightly polar, but methane has a perfect tetrahedral shape.
Like a pyramid with a triangular base, but all sides equal?
Kind of, yeah. It's perfectly symmetrical. So even though each CH bond has a small pull, they all point in different directions that perfectly cancel each other out in 3D space. Methane is nonpolar.
Wow. So geometry is destiny in a way for molecular polarity.
It really, really is.
This understanding of electron behavior also helps predict which ions form, right? You mentioned achieving a noble gas configuration.
Exactly. Atoms like to have the same number of electrons as the nearest noble gas because those configurations are super stable. So metals tend to lose electrons to get there. Calcium loses 2, becomes Ke2 plus Al like argon.
And nonmetals gain electrons.
Often, yes. Oxygen gains 2, becomes O2, electronically like neon. And then K2 plus an O2 attract each other to form neutral CaO. Or aluminum loses 3, Al3 plus. Oxygen gains 2, O2, so you need 2 aluminums and 3 oxygens to balance the charge, Al2O3.
And forming these ions changes their size, too.
Oh, absolutely. When an atom loses electrons to become a cation, like Ne becoming Ne plus No, it gets smaller. Fewer electrons being pulled by the same positive nucleus.
Makes sense.
And when an atom gains electrons to become an anion, like Cl becoming Cl, it gets bigger. More electrons, same nuclear pull, plus more electron repulsion pushes them out.
What about ions that have the same number of electrons, like O2, F, Na plus Mg2 plus air? They all have 10 electrons.
Good question. Those are called isoelectronic ions. For those, the size depends on the nuclear charge, the number of protons. They all have 10 electrons, but aluminum, Al3+, has 13 protons pulling them in. Magnesium, Mg2+, has 12. Sodium Na+ has 11. Fluoride F has 9. And oxide O2 only has 8 protons.
So more protons means a stronger pull.
Exactly. More protons pull the same number of electrons tighter. So in that isoelectronic series, Al3+ is the smallest and O2 is the largest.
Okay, back to ionic compounds. You mentioned the strong attractions in the crystal lattice. Is there a way to quantify that energy?
Yes, that's the lattice energy. It's defined as the energy released when 1 mole of an ionic solid is formed from its separate gaseous ions. And it's usually a huge amount of energy released. highly exothermic.
So making the ions might cost some energy.
Right, pulling an electron off sodium takes energy, ionization energy. Adding one to chlorine releases some electron affinity. Maybe you need to break F2 molecules apart. There are steps involved.
But the payoff comes when they snap together in the solid.
That's the key takeaway. The lattice energy, that massive release when the ions form the solid structure, is typically so large it overcomes any energy costs needed to make the ions in the first place. It's a driving force making ionic compound formation so favorable.
And does lattice energy also depend on charge and size?
Very much so. Just like Coulomb's law suggested. Higher charges mean much stronger attraction, much higher lattice energy. Think about magnesium oxide, MgO, Mga2 plus O2, compared to sodium fluoride, NaF plus F.
Both have ions roughly similar in size, but MgO has +2 and non-Q charges.
And its lattice energy is about 4 times greater than NaF's. That massive energy release for MgO is why it's stable with +2,2 ions, even though making Mg2 plus and O2 costs significantly more energy than making NaM plus and F. The lattice energy payoff makes it worth it.
That's a powerful concept. Okay, so we've talked ionic, covalent, polar covalent, all these ideas, bonds, electron pairs. They're useful models, right?
Yeah.
Not necessarily exactly how things are.
That's a really important point. Bonds are, in a way, a human invention, a model to help us understand why molecules stick together and have the properties they do. The localized electron, LE model, for instance, which treats electrons as either bonding pairs between two atoms or lone pairs on one atom, is a simplification.
But a usable one.
Incredibly useful. It allows us to think about molecules as being built from predictable parts, like CH bonds or OH bonds, which behave similarly in different molecules. It helps us organize and predict the chemistry of millions of compounds. But we always have to remember, models are simplified pictures. Sometimes they're wrong, and that's okay. That's how we learn and refine them.
And this idea of bond strength ties into chemical reactions too, doesn't it? Breaking bonds versus making them.
Absolutely. Breaking bonds always requires energy input. It's endothermic. You have to pull those atoms apart against the attractive forces.
Like stretching a spring until it breaks.
Good analogy. And forming bonds releases energy. It's exothermic. Atoms are moving to that lower, more stable energy state we talked about.
So in a reaction, you break some old bonds and form some new ones.
Precisely. And we can actually estimate the overall energy change of a reaction, the enthalpy change, or AH, by looking at the energies of the bonds broken minus the energies of the bonds formed. We have tables of average bond energies for different bond types, like CH, OESO, etc.
So you add up the energy needed to break all the reactant bonds, subtract the energy released when all the product bonds form.
And that gives you an estimate of whether the reaction will release energy, exothermic, negative H, or require energy, endothermic, positive H. For example, reacting H2 and F2 to make HF. You break HH and FF bonds, but you form two very strong HF bonds. The energy released forming those strong HF bonds is much greater than the energy needed to break the reactants, so the reaction is highly exothermic.
Okay, let's dig into that localized electron model a bit more. You mentioned visualizing electron arrangements.
Right, the main tool for that is the Lewis structure. It's a simple way to represent the valence electrons, the outermost electrons involved in bonding.
The rules are pretty straightforward, right? Count up all the valence electrons from all atoms.
Yep. Then draw single bonds connecting the atoms. Each bond uses 2 electrons.
Then sprinkle the rest around as lone pairs to satisfy the octet rule.
Mostly, yes. Hydrogen only wants 2 electrons, a duet. But for most other common elements like carbon, nitrogen, oxygen, fluorine, you aim for 8 electrons around each atom, the octet rule. You use lone pairs first, and if you run out of electrons before everyone has an octet, you start making double or triple bonds by sharing more pairs between atoms.
Like in CO2, you need double bonds between carbon and oxygen. Or in cyanide ion, CN, a triple bond.
Exactly. Those multiple bonds allow atoms like carbon and oxygen to achieve their octets. And it's crucial to remember, those electrons belong to the molecule as a whole, even if our model localizes them.
But you hinted models aren't perfect. Does the octet rule always hold?
No. There are important exceptions. Some elements, particularly boron and beryllium, often end up with fewer than 8 electrons in their stable compounds. BF3 is a classic example. Boron only has 6 electrons around it. This makes them electron deficient and quite reactive.
Okay, so fewer than 8 is possible. What about more?
That happens too. But only for elements in the 3rd period of the periodic table and below. Think sulfur, phosphorus, chlorine, xenon. These elements have emptied orbitals available in their valence shell.
Orbitals we don't usually worry about for carbon or nitrogen.
Right. These d orbitals can accommodate extra electron pairs. So sulfur in SF6 has 12 electrons around it. Phosphorus in PCl5 has 10. This is called an expanded octet.
So period 3 and below can break the octet rule by having more than 8. Got it. Any other weird cases?
Well, there are molecules with an odd number of total valence electrons, like nitrogen monoxide, NO. The Lewis model struggles a bit with these free radicals because you can't pair all the electrons up.
Okay. And sometimes you can draw more than one valid Lewis structure.
Yes, that often happens, especially with ions or molecules involving multiple bonds. Sometimes you have choices about where to put a double bond, for instance. This leads to the concept of resonance, where the actual structure is like an average or blend of the possible Lewis structures. But sometimes the possible structures aren't equally good.
How do we judge which Lewis structure is better or more representative?
That's where formal charge comes in. It's a kind of electron bookkeeping tool. For each atom in a Lewis structure, you compare the number of valence electrons it normally has as a free atom to the number of electrons it owns in the structure.
How do you count ownership?
An atom owns all its lone pair electrons plus half of the electrons in the bonds it forms. The formal charge is valence electrons, owned electrons.
And what are we aiming for with formal charges?
Ideally, you want formal charges as close to zero as possible for all atoms. Structures with large positive or negative formal charges are less favorable. And if you must have a negative formal charge, it's better to have it on the most electronegative atom, the one that likes electrons the most.
So it helps choose the most plausible structure among alternatives, like for the sulfate ion, SO42.
Exactly. You can draw it with all single bonds and satisfy octets, but that leaves large formal charges. Structures using double bonds between sulfur and some oxygens minimize the formal charges, even though sulfur expands its octet. Those structures are considered more significant contributors.
Okay, so Lewis structures and formal charge give us a 2D picture of electron distribution. Now finally, let's get back to 3D shape. You mentioned VSEPR.
Yes, the valence shell electron pair repulsion model. It's surprisingly powerful for its simplicity.
And the core idea is just electron pairs push each other away.
That's basically it. Whether they're electrons in a bond, bonding pairs, or non-bonding electrons, lone pairs, these regions of negative charge around a central atom will arrange themselves in 3D space to be as far apart as possible, minimizing repulsion.
So how do we use it, step by step for the listener?
Okay, first, draw the Lewis structure you need to know where the electron pairs are. Second, count the number of distinct electron groups around the central atom. Importantly, a double or triple bond counts as just one group because all those electrons are located between the same two atoms.
Got it. Single, double, triple bond all count as one region of electrons. Lone pairs count too.
Yes, each lone pair counts as one group. So step 3, arrange these groups in 3D space to maximize their separation. This gives you the electron geometry.
Like linear for 2 groups, trigonal planar for 3, tetrahedral for 4.
Exactly. And then step 4, look at where the atoms are positioned within that electron geometry. That gives you the molecular structure or shape. Step 5 is just naming that shape.
Let's visualize those basic shapes again. 2 groups.
Linear, 180 degrees apart. Think about CL2.
3 groups.
Trigonal planar, flat triangle, 120 degrees apart, like BF3.
4 groups.
Tetrahedral, like a pyramid, 109.5 degree angles. Methane, CH4.
5 groups.
It's a bit more complex. Trigonal bipyramid. Imagine 2 pyramids stuck base to base. You have angles of 90 and 120 degrees. PCl5 is an example.
In 6 groups.
Octahedral, like 2 square-base pyramids base to base. All angles are 90 degrees. SF6.
Okay, but those examples mostly had only bonding pairs. What happens when lone pairs enter the picture? You said they take up more space.
They do. Remember, lone pair electrons are only held by one nucleus, so their electron cloud is a bit more spread out, more diffuse than bonding pairs, which are pulled between 2 nuclei. This fatter lone pair pushes the bonding pairs slightly closer together.
Compressing the bond angles.
Precisely. Let's take ammonia, NH3. Lewis structure shows nitrogen with 3 bonds to H and 1 lone pair. That's 4 electron groups total.
So the electron geometry is tetrahedral.
Correct. But the molecular shape, described by the atom positions, isn't tetrahedral because one position is empty except for the lone pair. The atoms form a trigonal pyramid, like a short pyramid, and that bulky lone pair pushes the H&H bond angles down from 109.5 to about 107 degrees.
And water, H2O.
Oxygen has 2 bonds to H and 2 lone pairs. Still 4 electron groups total, so electron geometry is tetrahedral again.
But now 2 positions are occupied by lone pairs.
Right. The 2 hydrogens are pushed even closer together by the 2 lone pairs. The molecular shape is V-shaped or bent, and the HOH angle gets squeezed even more, down to about 104.5 degrees.
And that bent shape caused by the lone pairs is crucial for water's polarity.
Absolutely, it all connects back. The lone pairs dictate the shape, and the shape determines if the bond polarities cancel or add up.
What about those expanded octet cases, like xenon tetrafluoride, XF4? Xenon's a noble gas, shouldn't bond at all.
Well, the heavier noble gases can be forced to form compounds. XF4 has xenon bonded to 4 fluorines, and if you do the Lewis structure, xenon also has 2 lone pairs.
So that's 6 electron groups total, 4 bonding, 2 lone pairs.
Yep. 6 groups means an octahedral electron geometry. Now, how do those 2 lone pairs arrange themselves to be farthest apart?
Opposite each other, 180 degrees apart.
Exactly. They take positions above and below the equator of the octahedron. That leaves the 4 fluorine atoms sitting in a flat plane around the xenon. The molecular shape is square planar.
Square planar. And because it's symmetrical.
The polar XEF bonds cancel out. XEF4 is actually a nonpolar molecule, despite having polar bonds and lone pairs. Shape wins again.
Amazing. VSOPR seems pretty powerful. How well does it actually work?
It works remarkably well for predicting the general shapes of a huge variety of molecules, especially for main group elements. It's simple, intuitive, and usually gets it right. Are there exceptions or small deviations in angles it doesn't perfectly predict? Sure, it's a model, but its predictive power for basic geometry is fantastic.
Okay, wrapping things up then. We've journeyed through the world of chemical bonds. We saw bonds form to lower energy, ranging from ionic give and take to covalent sharing, with polar covalent in between.
We used electronegativity to predict bond polarity and saw how that polarity, combined with 3D shape predicted by VSEPR, determines if a whole molecule is polar if it has a dipole moment.
We looked at loose structures to map out electrons, saw the octet rule and its important exceptions, like expanded octets for elements in period 3 and beyond.
And touched on formal charge, helping choose between possible Lewis structures.
But stepping back, this isn't just lines and dots on paper.
Not at all. This understanding of bonding and shape is fundamental to, well, life. Think about enzymes, huge protein molecules. Their very specific 3D shape, determined by all the bonds and interactions within them, creates an active site that perfectly fits another molecule to catalyze a reaction. Change the shape slightly, it stops working.
And even communication between organisms.
Definitely. Animals, plants, insects release semiochemicals molecules with specific shapes that trigger responses in others. Pheromones are a classic example, like a queen bee controlling her hive, or chemicals plants release to attract pollinators or warn neighbors of attack. It's all about molecular shape and the properties arising from their bonds.
So the intricate dance of atoms, their bonds, their shapes, it dictates everything from how strong a material is to how life itself communicates and functions.
It really does underpin so much of the natural world.
So as you, our listeners, go about your day, maybe look at things a bit differently. Consider the invisible architecture holding it all together. What other secrets are hidden in the way molecules are built, just waiting for us to understand them better?
A lot left to discover, that's for sure.
Thank you for joining us on this deep dive into chemical bonding. Keep asking questions, keep exploring.